All right, we're going to get to problem 7. Let me read it first. It says, at what velocity and in what direction would a spacecraft have to be moving for a radio station on Earth transmitting at 100 megahertz be picked up by a radio tuned to 99.9 megahertz? Okay, so this involves what's called the Doppler shift, all right, or the Doppler effect, sometimes it's called. So let me go over the different variables for the Doppler effect. So lambda is the moving wavelength, and I'll explain what I mean by that. It's basically the wavelength that is observed when the source and the observer are moving with respect to each other, right? Lambda naught is the rest wavelength. That is when if you're just standing there and there's a radio station not far away, you're not in a car, you're not in a boat or anything like that, or you're not in a spacecraft, that would be considered the rest wavelength. You're not moving at all. All right. So we basically look at what the rest wavelength is compared to the moving wavelength, and that quantity is called delta lambda, the change in the wavelength. So it's going to be the moving wavelength minus the resting wavelength. And so the resting wavelength would be like, let's say that this is an antenna and it's broadcasting, and so there's a certain wavelength between the waves, and if this is, let's say that this is Earth and this is a spacecraft, kind of like the example that we're given, if the spacecraft were approaching the Earth, right? Think about what would happen to the waves, right? So if the spacecraft were approaching the Earth, the motion causes the waves to be closer to each other, right? So that's called the Doppler effect. You can actually measure that. That's a quantity that's easily measured. So that's if they're moving towards each other. And think about this quantity, lambda minus lambda naught, right? If lambda is the relative, or let's just call it the moving wavelength. If lambda is less than lambda naught, then you get a negative value, right? So this is negative, and that negative value is sometimes called the blue shift, right? The blue shift, and shift. That's supposed to be an F. I don't know. Anyhow, the blue shift is when they're moving towards each other, when the observer and the source are moving towards each other. All right. So think about what happens with the opposite situation, right? When the spacecraft would be moving away, as the spacecraft moves away from the Earth, here's the Earth over here. As the spacecraft moves away, what's happening is these waves that were, a certain wavelength apart, they actually get stretched, right? So the wavelengths, I'm going to exaggerate it here, the wavelengths start to look like that. And so there's a greater wavelength. So lambda, this quantity right here called lambda, is greater than lambda naught. All right, and so that the difference between the two, right? So this change in the wavelength would be positive, and that's called a red shift, right? That's a red shift, and so the red shift means that they're moving away from each other. All right, so we'll apply this to the problem that they gave us in just a second. All right, so I'm going to set it up. All right, so we're going to use this equation, of course, to calculate the wavelength. The speed of light is equal to the wavelength times the frequency. And so remember, we have two frequencies to deal with in this particular problem. One is the moving frequency that they gave us. In other words, how fast must ultimately we're going to try to figure this out. How fast must the spacecraft be going for you to get us for you to be able to tune in the radio station that is broadcasting at 100 megahertz to be brought to because of the Doppler shift, the frequency would be now tuned to 99.9 megahertz. All right, so let's do this first calculation to get the wavelength. Okay, remember this is lambda. This is the moving wavelength. It's 3 times 10 to the 5th kilometers per second divided by the wavelength. So I'm just changing the metric prefix mega to times 10 to the 6th, and then doing the calculation. So you get 0.003003, and it repeats actually 003. And notice the answer's in kilometers because 1 over seconds and hertz are the same thing. That's all hertz, the units of hertz are just 1 over seconds. So notice our lambda is 0.003, 0.003, and 0.003, right? It just keeps repeating. All right, well, what about lambda naught? So lambda naught is the rest. This would be the one where if you were on the Earth and there was a antenna that was broadcasting at 100 hertz, what would that wavelength be? 100 megahertz. So it would be the speed of light, 3 times 10 to the 5th. It's of course kilometers per second. Here I didn't really write that in. So it would be kilometers per second divided by 100 times 10 to the 6th hertz. And again, hertz and 1 over seconds are the same thing. All right, so they cancel. So that gives us a wavelength of a resting wavelength of 0.003. Now we know something. All right, we can actually answer this question. We can answer the part of the question that says, in what direction would the spacecraft have to be moving? Okay, so remember, if it was tuned to 99, if you tune the radio station on the spacecraft to 99.9 times 10 to the 6th, and you pick it up, it's still broadcasting at 100 megahertz. But because of the motion, the relative motion between the Earth and the spacecraft, you're able to tune it in at a longer wavelength. See, that's the important part, right? So 0.003003 is greater than just 0.003, right? Kilometers, of course. And so lambda minus lambda naught, the moving wavelength minus the resting wavelength, is a number greater than 1, right? And because that's greater than 0. That's greater than 0, and therefore you get a redshift. And what that tells you is they're moving away from each other. All right. So here's the image. Like if this is, let's say this is our antenna, right? And this is a huge antenna compared to the Earth. Here's our Earth. All right, here's the Earth. I don't have to really label that. And so what happens is because here's our spacecraft. I guess I'll put an S or something like that. The spacecraft doesn't tune to 100 hertz because it's moving away. The wavelength is a slightly greater. I exaggerated. Is slightly greater. And that makes them, the people in the spacecraft, able to tune into 99.9 megahertz. All right, so we know that they're moving away from each other. The spacecraft's moving away from the Earth. So in principle, we know that the Earth is we usually consider the Earth to be at rest, and then the spacecraft moving, but it actually turns out to be, it doesn't really matter. Either one can be moving, or they could both be moving, as long as they're moving away from each other or moving towards each other. Again, away from each other, it's redshifted, positive lambda minus lambda naught, and so that's redshifted. It means they're moving away. If you get negative, it's blue shifted, and they're moving towards each other. All right. So let's finish the problem. So now we need to know how fast is this? What's the velocity? What's the velocity of this spacecraft? We know it's moving away, but let's actually calculate it. All right. So I just realized in the last video I might have to just do that one or edit that one. In problem number, forget what it was. The one where I was talking about the Doppler shift, I think I might have, well, anyhow, I'll look back on it. If I remember, if lambda is greater than lambda naught, then that's red shifted. If lambda is smaller, then you get, you remember, you get a negative value for the Doppler shift. And all right, anyhow, all right, so this is the way they gave it to us in the book. Remember, this is exactly the same formula. Let me just write this again. This is the exact same formula as lambda minus lambda naught over lambda naught, right? That's exactly the same. And in fact, I actually like this one a little bit better. Anyhow, this, with a little bit of algebra, you can see that they're exactly the same. You just you replace the one by lambda naught over lambda naught, and then you get it to look like the one here on the bottom, this one here. All right. Anyhow, so let's solve for so if you take this top equation and you solve for the velocity, it's, you could do the same thing with the bottom equation, right? It's exactly the same here. Why don't I do that anyway? All right, so here's the bottom equation. We're going to solve for v. See, this is actually easier. The bottom one's easier to solve for v. You don't have to play around with the 1. It's just going to equal lambda minus lambda naught, over lambda naught, and that entire thing multiplied by c. See, that's exactly the same as this equation right here. All right, let's actually put some numbers in. I've been talking about this. Let's actually put the numbers in. All right, so here are the numbers. Now, I put both equations for you just to see. This is the version that's in the textbook. It's exactly the same as the version that I gave you. All right, so anyhow, there's the moving wavelength, there's the resting wavelength. You minus 1, and then you times that quantity times the speed of light, 3 times 10 to the 5th kilometers per second, and then and by the way, all the wavelengths cancel, right? All right, anyhow, so there's the moving wavelength minus the resting wavelength divided by the resting wavelength, and then you multiply. Anyhow, both times, both of these equations will get you. Try it. You'll see they give you the same result, which is a velocity of 300.3 kilometers per second. And that, just to give you a sense, okay, so here, I'll leave it to you to do this. You can do this if you want. 1 kilometer is, of course, I'm sorry, not 1 kilometer. Let's see, 1.6. I'm running out of time too. All right, so as I said, this is fine. Just come up with this 300.3 kilometers per second. That's fine. That comes from that equation. If let's say you converted this to miles per hour, because in the United States we're familiar with that. 1.6 kilometers is 1 mile. So notice the kilometers cancel, right? This kilometers cancels this kilometers, and then there's of course 60 seconds in a minute, right? So the seconds cancel, and then in 1 minute. Of course, in 1 hour there are 60 minutes, and so the minutes cancel. So you take this number 300.3, and you multiply by 60 squared, divide it by 1.6, and you come up with the following number. It's a rather large speed. So it's 675,000, that's 5, 675.7 miles per hour. That's supposed to be miles per hour. All right, so that is enormous speed. more than 6